Swayam Prabha. Digital India. Educated India.
Okay, now let us go to discuss generalized reduced gradient method. Now we have algorithm, specify the design and state variables, start with the initial trial vector x, identify the design and state variable y and z for the problem using the following guidelines. Number 1, state variables are to be selected to avoid singularity of the matrix D. Since the state variables are adjusted during the iterative process to maintain the feasibility, any component of x that is equal to its lower or upper bound initially is to be designated a design variable. Since the slack variable appear as a linear terms in the constraint, they should be designated as state variables. However, if the initial value of any state variable is 0, that is the lower bound value, it should be designated a design variable. So, compute the generalized reduced gradient. So, the generalized reduced gradient method is determined by using the equation G suffix r equal to del y f minus d inverse into C of whole transpose into del z f. So, the derivative involved in the equation can be evaluated numerically if necessary. Next, test for the convergence. If the all components of the CRG are close to 0, so the method can be considered to have converged and the current vector x can be taken as optimum solution of the problem. For this, the following test can be used, that is norm of GR is less than or equal to G epsilon, where epsilon is a small number. So, this relation is not satisfied, then we go to the step 4, determine the search direction. The CRG can be used similar to the gradient of an unconstrained objective function to generate suitable search direction S. The techniques such as steepest descent, Fletcher-Reeves, Davidson-Fletcher-Bowell or Broyden-Fletcher, Goldfarb-Shano method can be used for this purpose. For example, if the steepest descent method is used, the vector S is determined as S equal to minus GR. For the minimum along the search direction, although any one dimensional minimization procedure is discussed in this chapter, can be used to find the local minimum of F along with the search direction S. The following procedure can be used conveniently. So, subdivision A, find the estimate for lambda as the distance to the nearest side constraint. When design variable as are considered, then lambda equal to y suffix I power u minus yi of old if Si is positive. If Si is negative, then yi of L minus yi of old by Si if Si is negative, where Si is the ith component of S. Similarly, when state variable are considered, we have the equation dz equal to minus d inverse of C into dy. So, dy equal to lambda S, and then the equation gives the search direction for the variable z. Therefore, d equal to minus d inverse of Cs. Thus, lambda equal to ziu minus zi old divided by Ti if Ti is positive, zil minus zi old divided by Ti if Ti is negative, where Ti is the ith component of T. So, the minimum value of lambda is given by the equation, where lambda 1 makes some design variable attain its lowest or upper bound Similarly, the minimum value of lambda is given by the equation lambda 2 will make some state variable attain its lower or upper bound. So, the smaller of lambda 1 or lambda 2 can be used as an upper bound on the value of lambda for initializing a suitable one dimensional minimization process or procedure. So, the quadratic interpolation method can be used conveniently for finding the optimal step length lambda star. So, find the new x such that x nu equal to y old plus dy, and for corresponding z is z old plus dz, which is equal to y old plus lambda star s divided by then other part is z old plus lambda star t. So, this is the new vector can be determined. So, if the vector x nu corresponding lambda star is found infeasible, then y nu is held constant and z nu is modified and dz equal to z nu minus z old. Finally, when convergence is achieved with the equation, we find x nu equal to y old plus delta y and z old plus delta z and go to the step 1. So, this is the algorithm to be determined. Now, let us go example. Minimize f of x1, x2, x3 equal to x1 minus x2 the whole square plus x2 minus x3 the whole power 4, subject to the constraint g1 of x equal to x1 into 1 plus x2 square plus x3 power 4 minus 3 equal to 0, where xi lies between minus 3 to 3 and I varies from 1 to 3 using the G or G method. Okay. So, let us go with arbitrarily the independent and dependent variables as y equal to y1, y2 corresponding x1, x2, z equal to z1 which is equal to x3. So, let the starting vector x1 equal to, so according to the problem 2.6 minus 2.6 22 with the f of x1 equal to 21.16. Now, compute GRC at x1 noting that dou f by dou x1. So, differentiate this partially with respect to x1. So, we have 2 into x1 minus x2 into 1, therefore, 2 into x1 minus x2 will come, and differentiate this equation partially with respect to x2. We have minus 2 into x1 minus x2 plus 4 x2 minus x3 whole cube, and differentiate 1 partially with respect to x3. We have dou f by dou x3 equal to minus 4 into x2 minus x3 the whole cube, and differentiate 1 partially with respect to x3. We have this. Then G1 we know that this is G1, differentiate 2 partially with respect to x1, therefore 1 plus x2 square. Similarly, G2 you do that, you have 2 x1 x2 and then with respect to x3 4 x cube suffix 3. So, we find x1, the rule is delta y f equal to dou f by dou x1 dou f by dou x2 at x1. So, dou f by dou x1 already we found out, dou f by dou x2 is twice of minus 2.6 minus 2 plus 4 into 2 minus 2 the whole cube. So, which implies what? Minus 0.92 and this implies 9.2. Therefore, delta z f equal to dou f by dou x3 at x1 equal to minus 4 into x2 minus x3 whole cube into x1 square. So, we have value of c is nothing but the rule is dou g1 by dou x1 dou g1 by dou x2 at x1 is already we found the value of x1, substitute it, we have 5 comma minus 10.4. Similarly, d dou g1 by dou x3 at x1 equal to 32. Therefore, we have D inverse is equal to 1 by 32 D inverse and C. So, 1 by 32 into 5 minus 10.4, which is equal to 0.15625 minus other point is minus 0.325, because minus 10 by 4 divided 32 is we get this value. Therefore, GR is equal to del y f minus D inverse into C of transpose del ZF. So, we have del y f is minus 9.2 and this value is found out and this 0, multiply them, so that the same value will come. Since the component of GR are not 0, so the point x1 is not optimum. Therefore, go to step 4. The step 4 is nothing but steepest descent method and take the search direction S equal to minus GR equal to 9.2 minus 9.2. So, we find the optimal step length along S and consider the design variable, use the equation 7.111 to obtain y1 equal to x1, and we have a lambda equal to 3 minus of minus 2.6 by 9.2, which is equal to 0.6087. So, if y2 equal to x2, then lambda will be minus 3 minus 2 divided by minus 9.2 equal to 0.5435. Therefore, the smaller value gives lambda 1 equal to 0.5435. Now, the equation 7.113 gives T equal to minus of D inverse into CS. So, D inverse C is nothing but minus 0.15625 minus 0.325 multiply with 9.2 minus 9.2. So, the net value is minus 4.4275. Therefore, the equation 7.114 leads to Z1 equal to x3 and lambda equal to minus 3 minus 2 divided by minus 4.4275 equal to 1.1293. Therefore, lambda 2 equal to 1.1293. Now, we have upper bound on lambda is given by the smaller of lambda 1 and lambda 2, which is equal to 0.5435 by expressing x equal to y plus lambda x z plus lambda t. So, we obtain x1 x2 equal to minus 2.622 plus lambda times of 9.2 minus 9.2 minus 4.4275. Now, you know the simple addition of corresponding entry. So, that minus 2.6 plus 9.2 lambda, next one is 2 minus 9.2 lambda, third one 2 minus 4.4275 lambda. So, from this f of lambda equal to f of x, which is equal to minus 2.6 plus 9.2 lambda minus 2 plus 2 9.2 lambda the whole square, because x1 you know, x2 you know, x3 you know, substitute in the given function and then simplify, you have what? The quadratic in biquadratic in lambda value will get it. Now, you differentiate with respect to lambda, so that 4 times of this one equal to 2075.1225 lambda cube, and one more time differentiate, we have 2 times of 338.56 is 677.12. With respect to lambda, we have 169.28. So, the root of lambda star is approximately equal to 0.22. Therefore, lambda star is less than the upper bound value of 0.5435. So, we use lambda star we have the new vector new x new will come. The x new is y old plus dy, and corresponding z is z old plus dz. Therefore, y old plus lambda star x z old plus lambda star t is minus 2.6 plus lambda is 0.22 s value multiply, and similarly second one 2 plus 0.22 into minus 9.2, and third one will come. Simplify, you get this value, so that x new will get it. Now dy equal to corresponding value 2.024 minus will come, dz is this value will come. So we got all the values of dx, dy and dz, and now we check whether this vector is feasible. The rule is g1 of x new equal to x1 value, substitute it 1 plus of x2 square plus x3 power 4 minus 3, substitute it, you get negative value. Therefore, the vector is infeasible. Therefore, we have y new constant and modify z new by method of Newton method. We have dz equal to d inverse of minus gx minus c into dy. So, d is nothing but dou g1 by dou z1 partially with respect to z1 of g1 is 4x3 cube, and x3 value substitute it 4 into 1.02595 the whole cube. After simplification and multiply with 4, 4.31955 will come. So that the g1 of x equal to corresponding value we can write. Now c value is dou g1 by dou y1, dou g by dou y2 partially with respect to y1 do that of g1 and g1 with respect to y2 partially, and then we have the values of what x1, x2, x3 and corresponding y1, y2 also given, substitute it and you get the values is minus 1.104 and minus 3.5258 will come. Once you get c value, go to the dz. The rule is 1 by of d of the value x1 minus of x2 comma the point c into the vector, so that the resultant is minus 0.5633. So, we have z new equal to z old plus dz and substitute it. Z old is nothing but 2 and dz is just now we got it and subtract it, you get 1.4367 will come. Therefore, the current new value is nothing but y old plus dy and z old plus dz. Y old dy z old z dz found out, substitute it, you get the corresponding x new will come, and these values substitute in the constraint of g1. So, the answer is positive and is not equal to 0. Therefore, the new is infeasible. Now, apply Newton's method of the current x new. So, the present case, instead of repeating Newton iteration, we can find the value of z new equal to x3 new by satisfying the constraint g1 of x equal to substitute corresponding x1, x2, x3 value, so that you can get the value of x3 equal to 1.2477. So, x new is x1, x2, x3 value got it, substitute it and substitute this value in the given function, you get 2.9201 will come. Therefore, you go to the step 1. Step 1, we do not have to change the set of independent and dependent variable. Therefore, go to the next step and compute G or G and the current x using the equation. Since del yf equal to dou f by dou x1, dou f by dou x2, you take f partially with respect to x1, you get it. You take f partially with respect to x2, you get it this value. After simplify, you get these two values, minus 1.104 and minus 7.1225. Therefore, del z f equal to dou f by dou z1 equal to dou f by dou x3. So, we have the value that is the corresponding del z f. Now, C equal to dou g1 by dou x1 and dou g1 by dou x2, g1 partially with respect to x1 and g1 partially with respect to x2. So, that corresponding dou g1 by dou x1 value and dou g1 by dou x2 value will come. After simplify, C having the two values. Similarly, you go to the mod D or box D dou g1 by dou x3. So, partially with respect to x3, 4x3 will come. x3 value you know, substitute it so that you can get the value. Now, you take the inverse of D, therefore, 1 by of this will be 1 by of this, C you know. So, these values substitute here and divide them, you get two values, one is 0.128, another is 0.003. Now, we have to use the GR. GR is del yf minus D inverse C transpose into del zf, and del y substitute it. D inverse C got it, that you have to take the transpose, so that the value will come. Del zf is this value, and now this is 2 rows 1 column, 2 rows 1 column. Multiply this and simplify, you get minus 2.1634 and minus 7.1518. Since GR is not equal to 0, we need to proceed to the next step. Now, we have a note, the objective function reduced from an initial value of 2.16 to 2.19201 is one iteration.